In this lecture, I'm going to give a brief introduction about the course linear system control. So, as we know from the name of the course, so this linear system control, so it composed of two aspects. One is the control, one is the linear system. So when we talk about control, actually we mean by mainly two things. One is called analysis, one is called design. So the control, the analysis part of the control is to figure out if I give a system, what is if I give a system and also give an input, so what is the output. The control design talks about if we have a goal that we specify and how we would design the control input that can meet the goal, or we can optimize the goal by designing the control input. Okay, so that's kind of the two aspects of the control. So here we talk about linear systems. Linear system is a kind of special type of system because we can have a linear system, nonlinear system, or even more complicated system not described by linear nonlinear system. Okay, for example, when we talk about the stochastic system, which can be a little bit different. So generally speaking, linear system is a type of system which is a little bit special, so it's a little bit easy to analyze to talk about the control aspect. So when we talk about linear system, there are a couple of properties that are required to be satisfied for linear system. So one is called Additivity Property. So in other words, for example, if I give a system G, this is called block diagram, given in the undergraduate control class. If you take the class, you should know my notation here. So G is you can consider as a transfer function. So G for a given system described by G, and if I give input U1, let's say you get an output which is Y1, and for G it's the same G if you give it U2 and the output is Y2. So this property says if I give the same G, if I give U1 plus U2 as the input, and the output will be Y1 plus Y2. Okay, so this property basically says if you sort of increase or decrease your input by a certain amount, for example U2, then the output will be proportional to, will be just based on the differences. Okay, it doesn't matter what the base is about, actually it's the difference matters. So this is the additivity property. The second property is the homogeneity property, which means the property says you can scale it up and down. Assuming you have a original system G, you give input U1, the output Y sub 1. You can scale your input by alpha, either up and down. So the output will also be scaled by the same number. So you basically can scale your input and by getting a scaled output. Okay, so that's kind of two property we talk about for the linear system. Okay, of course later on we talk about linear time invariant system. There will be one additional property for linear time invariant system. Okay, all right. So to give idea about what control is about, let's talk about a simple example. What do we mean by analysis? What do we mean by design? Later I'll talk about the two. Give examples showing you what we mean by analysis. What do we mean by the design? So for the control part, let's take a look at what is the control about and give you a simple example to see what is the control analysis and what kind of tools that we can use to solve, to get the control analysis part down. Okay, so the control, as I mentioned before, the control analysis basically talk about if I give you a system G and give you an input, and my goal is to compute the output. So that's the goal of the control design, control analysis. So typically the system is represented by the ordinary differential equation, especially for linear system. Typically we can write this as an ordinary differential equation. So the main goal, the main problem is how do I obtain a output y to give an input u sub t. So give a more explicit example about what this problem is about in general and how we solve the problem. I give you a very simple example. So here talking about an object which is M, so it's sitting on a surface, okay, and I label the direction on the surface to the right as Y, so this is the direction of the positive direction of the Y, and also there's a vertical wall on the left hand side. You can consider it as this. So there's a spring attached to the wall and also the other end of the spring attached to the object. You sort of can see if I apply a force of U on the object probably going back and forth. So it will move to the right and maybe go back and forth. Okay, so that's kind of what's going to happen. So our goal is trying to figure out if I give certain u, this is u is my input and y is my output. Okay, here also assume there's a friction between the object and the floor, the surface. So the coefficient is given by k1, which means this is depending on the velocity. The faster the friction will be larger. Okay. So once we have this, we sort of can see, we can sort of write as we first need to get as a system described by the ordinary differential equation, which actually characterizes the relationship between the input and output. Okay. It's not difficult to figure out the relationship between input and output by using the ordinary differential equation. As a matter of fact, this is given by Newton's law. It's like m times y double dot. So y double dot is called, you can view this as acceleration because it's going along the direction. This is acceleration. So m times acceleration, this should be the force applied to the object, which is the u. Apparently there's a force applied to it. And also I have to minus the force created by the friction and also the spring. So the force created by the friction is negative k1 times y dot, okay, and the force created by the spring is given by negative k2 times y. So that's the spring force. This is the friction force, okay, created by the friction. So as you can see here that the input u over here, okay, and the output y, they are sort of related. They're described by a differential equation, which is exactly what we mentioned over here. So our goal is to say if I give you the u, okay, how do I figure out what is my y? Apparently the y is not a static, it can be a function of t. Okay? Alright, to make it a little bit simple, let's consider a case, give some specific number for this the mass of the object, the control input, the k1 and k2. So I assume here k1 and k2 are 1, and also mass is 1 to make it simple. I want to see, hey, how do I compute the output given certain input? Okay? To be more specific, let's talk about the input. U sub t is given by unit step input. So assuming here that when t is less than 0, so I don't have any input. When t is greater than or equal to 0, then I have the input is a constant, which is 1. Which you sort of can see my u is just 1, it's constant. Okay? So my goal is trying to figure out, hey, what is my y sub t? Okay, so that's kind of the question we're talking about. So given certain input, given a system, described by ordinary differential equation, and what is my output? Okay, so how do we solve this problem? Okay, of course, one direct approach, we probably can solve the differential equation directly. If I can solve the differential equation directly, which is fine, I can find a solution. Okay, one typical approach we talk about in the undergraduate control class, if I've taken the course before. So the typical approach is to use the Laplace transform and inverse Laplace transform. Okay, so please go and review the Laplace transform, inverse Laplace transform if you have questions about it. So we wouldn't be able to review those in this course, but you can find those materials online, or I can point out some of the references for you to look at. So the general idea for this one is because the differential equation here is a little bit hard. This should be double dot. So solve the differential sometimes can be challenging, especially if I have higher order derivative. This is a double derivative, it's not so complicated. However, if I move to the triple derivative, it can be very challenging to find a solution. Okay, what the Laplace transform and inverse Laplace transform do is to convert the differential equation into another equation, which is much simpler than the differential equation. So the Laplace transform, what it does is try to convert the time domain, which is the differential equation we're talking about over here, then move it to another one domain we call the S domain. Okay, then we can compute this transfer, what do we call transfer function. This is all described in the undergraduate control class, is 3413. Okay, I'll talk about this in a minute, right over here, to talk about the steps. So once we transfer to the S domain, we don't have derivative anymore. We just have products, plus and minus, which we know how to solve relatively easily. So once we have that one, we can find the output in the S domain. Okay, by computing first the transfer function and time my input. Input also has to be converted in the S domain. Okay. Then once we figure out the solution in the S domain, we can do the inverse Laplace transform to find the output in the time domain. In other words, we don't do the solve the differential equation anymore. We just need to convert to S domain, find a solution to S domain, then do the inverse Laplace transform to find a solution in the time domain. Okay? Alright, now let's take a look at the specific example to see how we apply Laplace transform, inverse Laplace transform to find a solution. Okay? So Laplace transform has a note. Typically we use the notation called, we use this notation called L of whatever, let's say y sub t, okay, as Laplace transform. Notation wise, we also use this as big Y of S. So for example, I have L u sub t is also the Laplace transform that my input is the big U of S. I can also have this L, you can add any other variable, let's see, xt, okay, so it doesn't appear over here. You can also notate it as big X S. Okay, so that's the typical way people describe the Laplace transform, and also how we simplify the notation. Okay, use bigger uppercase for the same variable and of S to represent its Laplace transform. Okay, so here let's say I can apply the Laplace transform on both sides of this equation, which is given by here. Applies the Laplace transform on both sides. Okay, Laplace transform on both sides. On left hand side is y double dot, right hand side is L of u minus y dot minus y. Okay, so right hand side the Laplace transform has a property of linear property, so you can kind of separate those because this is u minus this guy, so you can say it's L of u. You can put the minus outside, minus ly dot minus ly dot ly. So that's it. So if I define this ly as y sub s, okay, over here, okay, you can define that way. So the left hand side, the typical, this is from the this is ly double dot. This is you from table. If you look at the Laplace transform of the table, okay, you can find the y double dot is s squared times ys minus sy0 minus y dot 0, and ly dot is s times ys minus y0. Okay, let me just make it a little bit clear. This is y0. Okay, so pay attention to here. This is big Y and this is a little y. Okay, this is still little. This means it's yt in the time domain. Okay, it's not a big Y. Okay, and lu is just use of s. Okay, here I drop all the t. It should be lut. I drop all the t. So u is use of s. Okay, and L1 is 1 of s. This is also from table. You can find out. So L1 is 1 over s. Okay, so by doing this, so we can simplify this a little bit. So if we look at it, this one, if I pull this one, write one, compute it specifically, so I have s squared minus times ys minus sy0 minus y dot 0, which is, so ys is, which is equal to, so that's right. I'm sorry, we should say this. So let's do this, the whole equation right over here. Okay, so the left hand side is the ly double dot, which is s squared times ys minus sy0 minus y dot 0, which is right over here. Right hand side is lu. Okay, u is 1, so L1 is 1 over s, so this is lu, and minus ly dot. Ly dot is this, right? So it's minus sy, so this should be this, okay, and minus ys, so this is ly is 1 minus ys. Okay, all right, so when we do that, we have s squared, so we can just clean up a little bit. So we put all the ys to the left. Okay, with the ys to the left, so I move this term to the left, this term to the left. Okay, so I have s squared ys plus sys plus ys. Okay, so I move this one to the right hand side. Okay, so I have is 1 minus 1 over s minus sy0. This time should be plus y0, and this is this one should be correct. So this one should plus 1s0 and plus y dot 0. Okay, then I have one more is here is I have one more term plus y0. Okay, all right, so this one has s squared plus s plus 1 ys. This one become, okay, right over here, which is plus sy0 plus y dot 0. We can combine these two together, so s plus 1 y 0 plus y dot 0. So those are based on the initial conditions, which means I have what is y0, the initial location, which means what is the initial location right here of this object, and y dot 0 is the initial velocity, which means at the very beginning what is the velocity of this object. So that also those two also play a role in determining the y sub t. Okay, so we sort of have this. So right over here is I should do this. Okay, this is plus s plus 1 y sub 0 plus y dot 0. Okay, so here let's do this one. Okay, let's do this one. So it's right over here, and once we have this one, so we can compute y sub x actually, because we divide by this this part. We move to the right hand side to divide by this whole thing. This becomes, if we assume here y0 is 0, okay, y dot 0 is 0, which means initial values are 0, so which can be simplified as this. So this will be gone. This will be gone basically. So then we can find the solution y sub x given by this. So this is the whole stuff going from here. Linear differential equation, we compute, actually we combine these two steps. We compute transfer function. Actually, we don't have to compute transfer function. So we actually are direct compute the solution in the S domain. Now we're left with computing the output y sub t in the time domain. We just need to use an inverse Laplace transform. Okay, so inverse notation wise using by this is L inverse of y of s. This will give us y sub t. Okay, so it's L inverse of this guy. Okay, is this y, which is put over here. Okay, so to solve for the y sub t by using the inverse Laplace transform, the main project we're using is called partial fraction expansion. The idea is we try to split. So this is very hard to say, but I can split this one as a over s plus bs plus c over s squared plus s plus 1. You basically want to make it a little bit simple because I know how to do this. This one I know what is it. Once we do this, the linear property of the inverse Laplace transform says this is the L inverse of a over s plus L inverse the second term. Okay, so for the first one, we already know what is this is by using the table. So this is we're using the table. We know what is the a over s, what this means. Okay, of course I still need to figure out what is the a and b and the c, right? So the idea to figure out a and b, c and c is you do a over s plus bs plus c over s squared plus s plus 1 equal to 1, because that has to be equal to this one, 1 over s squared plus s plus 1. Okay, you want to compute a and b and c. Let's compute this. This one is given by s squared plus s plus 1. Okay, so the numerator will be given by, if you put the common s times this as the common denominator, so this numerator becomes a times s squared plus s plus 1. This will become bs plus c times s. So this one must be equal to this guy, right? So which means we have this as squared plus s plus 1 plus bs plus c times s must equal to 1. Okay, must be equal to 1. So if you look at this, so which means if I simplify this is a s squared, right? Plus as plus a plus bs squared plus cs. This must equal to 1. So it means this one you can say is 1 plus, this is also means is equal to 1 plus 0 times s plus 0 times s squared. So which means the coefficients we said over here is this guy a must equal to 1, okay? And also the coefficient for s squared 0, which means if I do the coefficient for s squared, you put them together, right? Right over here, so here a plus b, so a plus b must be equal to 0, okay? And also I have this one means b is negative 1. The last one says a plus c is equal to 0, so C is negative 1. It's also negative 1. So you sort of see this B is 1, B is negative 1, C is negative 1, so this A is 1. You can see that. So once you do that, you can follow my steps. Over here is A over S plus L inverse BS plus C divided by S squared plus 1. So this one you have to use a table again. If you look at the table, so I don't want to talk too much about it, how to do the inverse Laplace transform, but if you do have questions, you can let me know, okay? So you write this one as something like, you write the denominator as S plus A, I don't know, A is W squared plus use something like this form, okay? The numerator has to be divided to be rewrite this as some B time this one must be equal, has the same form, and then you have a constant somehow over here, okay? Once your table, you can figure out this is just A plus B negative E minus 1/2 T cosine square root of 3 over 2 times T plus C minus 1 over B square root of square 3 over 2 times E. This will be your final solution. This is what is the y of T, okay? Of course, I haven't plugged in the A and B and C value. You can plug the value A is 1, okay? So here A is 1, A is 1, B is negative 1, okay? C is negative 1, and B is negative 1. So this will be negative 1/2 basically, okay? Then that's the solution. So that's the solution to this problem, which means this is how the YT will change. It's not straightforward. It's probably going to back and forth and stabilize at a certain point. Okay, this is how we solve for the problem. This is the previous example. In here, we're talking about a single input and single output system. What about if we have multi input and a multi output system? You can still use the Laplace transform, inverse Laplace transform to find the solution. So let's say I give you here's example about the multiple input and multiple output system. So here I give you a system which is x1 dot x2 dot, which is equal to this matrix times x1 x2. I call this the A matrix plus B matrix times u1 u2. Okay, so here you say I have two inputs, u1 u2, and my output is y1 y2, which is the matrix C times x1 x2 plus this matrix D times u1 u2. So basically I have multiple input and I have multiple output. Okay, so I sort of can define this x as a column vector x1 x2, y1 y2, u1 u1 u2. So you basically can write this as x dot, which is ax plus bu, and y is cx plus du. So this is a very typical form for the linear system. Okay, is x dot is x plus bu and y is cx plus du. Okay, so of course the input we have multiple inputs and multiple outputs. Okay, to find the solution of the y, given input, what is the output? You can also apply using the Laplace transform, inverse Laplace transform. So only difference here, we're talking about a matrix and vectors, not just directly a differential equation. Okay, so let's say we do Laplace transform for both sides for the first equation, which is given by this. Okay, so you apply Laplace on both sides, both equation, which is same as the Laplace on this. The same together, so the same as the Laplace on the right hand side. Okay, and similar for the second equation. Okay, we do have this, it becomes this. You also apply the Laplace transform on both sides. So that's it. So once you have this, you sort of can see, if I use the notation what I defined over here as a notation, you also can simplify the whole thing by x dot with x plus bu, y cx plus du. If you do that one, you can apply L on both sides. Laplace transform both sides. So this will convert. So for this one, you sort of can consider this x as a scalar case. Use the same property I mentioned before, like Lx dot. You will sort of assume this is just a scalar, but use the same property. The only difference is when you do the actual calculation, it has to be a vector. Okay, so sxs minus x0 equal to a times xs and b times u sub s. And here we can find out, assuming that the initial state is a 0 or 0, make it simple. So xs will be just s times a inverse times b times s. So this is different from the scalar case. Scalar case, you have s minus a. You probably have b over s minus a. times u sub s, something like this. Okay, but here you have si minus a inverse b times u. So this is called identity matrix. So I talk about all the notation in later on. Okay, if you don't know, understand what I mean by here, it's okay. I'll give you a review of some mathematical notations and some of the matrix properties before we go to the detail about how to find the solutions. Okay. So once we figure this x of s, we can find a y sub s, which is cxs plus dus. So xs we already computed right over here, so you can plug in the xs into here. So we have c s minus a inverse bus plus dus. This one is also the same as c si minus a inverse b plus d times u sub s. You can combine them together. Okay. So apparently y sub vector, you can do the inverse Laplace transform, you can find a y sub t. Okay. So this one apparently here y sub vector is u. So when you compute a y sub s, y sub somehow like this. Somehow like this. You have, let's say you have a previously I have two, right? I didn't give the detail of the computation, but you probably have something like something divided by something and also something divided by something. When you, this is what you get a y sub s right over here. When you do the inverse Laplace transform, you have to do the inverse for individually. For this individually, find a y sub t. Okay, find some t. Of course, this is a typical we can compute it. After I talk about the solutions, the control analysis for linear time system, you don't have to do these steps. There will be analytical solutions I can give you for the A and the B and the C and D. I can give you analytical solutions about this one after you're talking about the mathematical notation computations later on. Okay. Okay, so that's much about what I want to describe about what is the control analysis components. Okay, so give example how we use the final solution for linear for a given control system and a given control input. Okay. Now talk a little bit more about the linear system. What property define the linear system? As I mentioned before, the linear system has two properties. One is called additivity. One is homogeneity property. So you can refer to my very beginning of my video, this video, about what these two properties mean. Okay, so when we talk about linear time invariant, linear system, we talk about two types of system. Okay, they're different because the way we compute we do the control analysis can be a little bit different. So there are two types of systems. One is a linear time invariant system. One is a linear time variant system. They share the same common properties that I mentioned over here, additivity and homogeneity. They also have one differences between them. Okay, so for example, what do I mean by linear time invariant system? What do I mean by linear time variant system? So linear time invariant system is sort of like this. You have y sub dot t is 2yt plus 3ut. This is called linear time invariant system. The reason we call linear time invariant because all the parameters, you can consider this as one time one dot y dot t. This is one time one dot t. So you sort of see all the parameters over here, they are constant. So this parameter is 1, 2, and 3. They're constant, which means they are time invariant. So this is called time invariant system. On the contrary, if you look at this system, which is given y dot t, which is t times yt plus 3ut, this is called linear time variant system because if I look at the parameters, this is 1, it's constant. This t is not a constant. It's time variant because at different time this will be different. And this is 3. So you have 1, t, and 3 are the parameters, so they're not a time variant. So this is a linear time variant system. So as a matter, we don't have to have everyone to be time variant. As long as one of them time variant, we call it time variant, linear time variant system. Okay. So one of the key properties, the difference between the linear time invariant system and linear time invariant system is one extra property we can have for the linear time invariant system. So the last property for the linear time invariant system is called time independent. This is only true for linear time invariant system. So it's not true for linear time invariant system. Okay, what time independent says, you can shift your input by certain amount. For example, if I shift my input of UT by delta t, and the output will also be shifted by the same amount of delta t, which means, let's say if this is my input, okay, and my output is somehow like this, okay, so if I shift this input by delta t to the right, my output also shifted by delta t to the right. You can also shift to the left and shift to the left. It means that it's the same product apply, which means it doesn't matter where you start. And if you give the same shape of input, same input, I will have the same output. Okay, and they're also shifted by the same amount. This is called linear time. This is called a time-independent property for the linear time invariant system. Okay, here I'm going to stop over here. So next lecture, I will talk a little bit more about the linear system property, and then we'll go to the mathematical background part.